Hello, welcome to Lecture 4, in which we discuss pedigrees, the chi-square, and conditional probability. Okay, up until now I've been doing a lot of work, actually focused largely on Drosophila and pea plants, in which a researcher can basically set up any cross they want. For example, in the case of sex chromosomes, a male is mated with a female, the daughters were collected, and then those daughters were back crossed to the male, the original male. Um, with humans, you can't do that kind of stuff, obviously. So what you can do, though, is you can analyze what are called pedigrees, which are basically genealogical relationships among members of a family. All right. So to understand how to interpret pedigrees, it's important to be able to look at the symbols that are being used. A square would indicate a male, and usually an empty one, all of these individuals are empty, indicate that they might not be affected or they're not affected by the usually a disease, to be honest with you, but the phenotype in question. So squares are males, uh, circles are females. A mating would be shown this way, and then you would have two parents who have offspring, a boy here and a girl here. If you wanted to show non-identical twins, so for example, if independent gamete fertilizations occurred within a woman, two sperm and two eggs, those would be non-identical twins. But you could also show monozygotic or identical twins this way. And then if the sex is unknown, for various reasons, it could show it that with a diamond. All right. Affected individuals are shown with filled-in colors. If you know that an individual is homozygous for a recessive, you can show a half filled-in circle or square. If there's a carrier of a sex-linked recessive, you can show it with a dot, and then this indicates death has occurred. This is a case where the sex is unspecified because maybe the baby died during pregnancy. The focal individual would be here, and then within a larger pedigree, you'll have generation 1 and generation 2, and then the double lines show what are called consanguineous marriages, basically marriages among relatives, so a form of inbreeding. When we talk about pedigrees and we analyze pedigrees, there's a couple of things that I want you to remember and sort of take into mind, because sometimes you'll stare at a pedigree and be like, well, there's a lot of things I don't know about it. But if you make these assumptions, it becomes a little bit easier. First off, the harmful or disease alleles are rare. All right. And what that means for the purpose of this course, unless specified, all right, you can assume that there's only one harmful allele segregating in the pedigree. And so, to be clear, unless specified, you can assume that individuals from carrier families, so you have a family that might carry a recessive mutation, when individuals in that family reproduce with other individuals, they will be usually mating or reproducing with non-carrier families. And of course, the exception is in mating among relatives, because then that's within a family. So a rare allele could be present in those two individuals because they're within a family. Okay, so the way we break this down is we look at common patterns of inheritance. And the first one we'll discuss is a dominant mutation that resides on an autosome. So by autosome, I mean not on a sex chromosome. And probably one of the most famous dominant diseases caused by a dominant disease allele is Huntington's disease. Huntington's disease is a neurodegenerative disorder. It can hit you when you're in your 30s or 40s or 50s, and basically it causes the nervous tissues to break down. And you can see, for example, the brain of an individual that's normal or the brain of an individual that's Huntington's disease. You can see that there's a big difference. Now, Huntington's disease is caused by a dominant allele that, remember we talked about like a dominant poison, for example. It's basically a dominant poison. What it is actually it's a protein that doesn't fold properly, and it causes other proteins to stick to it. It causes aggregates in the cells of the nervous system, and those aggregates cause all sorts of downstream problems. This is an example of a pedigree of a family in which there is a Huntington's disease allele that is being transmitted from generation to generation. And because it's dominant, everybody who has that mutant allele has the disease. So we start off with this individual here has the big A, little a. In this particular case, the big A allele, is dominant, right? And it's the mutant allele, right? And there's only one big A allele floating around in this pedigree because it's rare. So this individual, there's a 50-50 chance of passing it off to either of their offspring. And so this individual has 1, 2, 3, 4 offspring, right? And of those, 2 of them have inherited, which is what we might expect, and 2 of them have not. Now, of course, because this individual is little a, all of the individuals inherit the little a from this mother. Now, in this particular case, any individual that has this mutant allele can pass it off to their progeny, and half of their progeny will be expected to have that. So there's some typical rules for dominant autosomal alleles, such as the Huntington's disease gene allele. Females and males are equally affected. Affected offspring have 1 affected parent, all right, 1 because it's rare, so you wouldn't expect 2 just to randomly have this disease. And then on average, now obviously this is not going to be always the case, but on average, half the number of children of an affected parent are affected. Okay. Another pattern that one observes is in the case of, say, for example, albinism. So this is a person who the family would have had dark skin, but this person has lighter skin because they have albinism. And in this particular case, you'll see basically it showing up oftentimes in cases in which there's been some sort of inbreeding of some level, but this is not always going to be the case, but it can show up in that case. So in this particular case, this individual, now the recessive autosomal allele is little a designated here, right? So this individual is big A, little a, and big A, and neither of these individuals is affected because it's recessive. Now this little a allele can be transmitted to the offspring, all right? Not all of the offspring will have received it. So for example, this individual may not have, but this individual transmitted it to the daughter and then to the son. And notice something here, right? So this daughter and this son, they have children. These individuals are cousins, and because they inherited this little allele from this grandfather up here, got transmitted, and now you can see the phenotype due to homozygosity for the little a allele in these cases. All right, so there's some little rules that you're worth thinking about for patterns that you see in pedigrees for recessive autosomal alleles. 1, females and males are also equally affected. Affected individuals that are little a, for example, usually have unaffected progeny. And they usually have unaffected progeny because they're not usually reproducing with someone who's a carrier. All right, most affected, by carrier I mean an individual who's heterozygous. Most affected individual, little a, have unaffected parents because the parents don't know that they have this allele that they're carrying. The parents of affected individuals are often relatives, which is what I just showed you in the last thing. And among siblings with affected individuals, 25% approximately are affected. So if you had a cohort of, say, 8 siblings, you might expect 2 of them to have it, right? If one of them has it, then that means the parents are heterozygous, and so any additional children, there'd be about a 25% chance that they would have it. Then, with respect to sex linkage, one can also have an X-linked recessive allele, all right? And in this particular case, this individual, this male, is hemizygous, and so has the mutant allele little a here, and this individual would have had children with an individual, a female that's homozygous for the wild type. Now, it's sex-linked in this particular case, and so you can sometimes show a little dot there indicating that this individual here is a carrier, and you know that's the case because the daughters, all right, this female always collect the X chromosome from their dad, right? And so if the dad has a X-linked recessive allele, you know that the daughters are a carrier. All right, now the daughter's unaffected by the disease because in the case of hemophilia in this particular case, but the daughter's unaffected by it because she has the wild type copy that she collected from her mother. Now, if this female here has children, with a wild type male, right? Half of her sons will collect that X chromosome that has the mutant allele in this particular case for hemophilia. Now, all the daughters are going to be protected by the X chromosome that's wild type from their dad, but the sons are not going to be protected because the Y chromosome doesn't have effectively any genes on it, and so the sons only collect one mutant, one of the X. The sons collect the X chromosome from their mother, and half of those will be the mutant, and half of them will not. So the rules for that are males are usually the only ones affected, but that doesn't mean it's always the case. The affected males, all right, that are little AY have normal sons because the affected males transmit the Y to their sons, and the sons collect the wild type allele from their mothers. And the daughter of an affected male has affected and unaffected sons in a 1-to-1 ratio. All right. Okay, so hemophilia is very famous in the context of the European royal families over the years. In this particular case, this is a very large pedigree, and there's a significant amount of inbreeding to various extents within royal families, but that's not the particular cause in this particular case here. But there's actually a very famous, case where hemophilia was transmitted across many, many, many individuals, and it had a lot of repercussions during the royal family's history in the last part, especially of the last century and before. Okay, so we're going to walk through a couple little questions. I want you to think about them. So in this particular case, what is the genotype of individual 3-5? So I'll let you stare at this for a second. Okay, so you have A, B, C, and D. Let me just see if I have the answer. No, I don't have the answer. So I'll just tell you right now. This individual here, 3-5, you can see that there's a form of inbreeding that has occurred, and you can also see a pattern in which, amongst those individuals that were the result of that inbreeding, about half the progeny have this phenotype, and that is consistent with it being recessive allele, and it would be consistent with it being autosomal because both the male and the female have it. But this means that because these individuals have this mutation, if they're big little a, for example, then that would mean that the parents had to have been heterozygous. So the best answer here would be B, big A, little a, for individual 3-5. Okay, what about that's the one we just did. Okay, what is a genotype of 2-1? Okay, I think we've done something like this already here. In this particular case, the answer is not a good answer there because, backing up. This individual, this is what we showed already here, where there's a pattern of sex linkage. The males have it, it skips a generation, and in this particular case, 2-1, well, in this particular case, it's a male, so actually none of those would actually be a good answer here, so because we would want to indicate a Y chromosome. And they're unaffected, so we would say, in this particular case, that this individual would be, say, big DY. Okay, now the female, of course, would be big D, little d, because she is a carrier. So 2-2 would be big D, little d. Okay, so that's the one that we just did as well. Okay, so just as a quick breakdown, there's going to be a few homework assignments on this, but you'll be able to want to work through some of these pedigrees and make inferences about the different genotypes. Okay. Now, we've been looking at, I'm going to change gears a little bit right now, switch gears for a second. We've been looking at outcomes of crosses in which we make particular predictions. And in this particular case, you might do, again, we'll go back to those P's, round and wrinkled. You collect the F1 generation, and you can do some crosses and selfing, and you might count certain numbers of plants. Now, in this particular case, all right, when we self these individuals, we expect a 3-to-1 ratio. All right. Now, you can count certain numbers of plants. So you can count as many plants as you want. Now, what I want to actually ask and have everybody think a little bit about is that if you expect a 3-to-1 ratio, would you be able to look at things that look like deviations and say, okay, something's weird going on. Maybe there's some sort of pollen viability problem. Any other particular case, any other particular scenario that would suggest that something's going wrong and there's not, in fact, a 3-to-1 ratio. Now, if you just had 4 plants and you observed 2 round pea-bearing plants and 2 wrinkled pea-bearing plants, you would expect, well, if there's a 3-to-1 ratio, you'd expect 3 round and 1 wrinkled, and you observe 2 and 2. Would you be willing to say that this is inconsistent with the expectation? And of course you wouldn't. You'd be like, well, that's pretty darn likely. All right. Now, you could grow up a larger number of plants, for example, 24, and in this particular case, the exact numbers, again, maintaining a 3-to-1 ratio, but the exact numbers would be 18-6. And you might observe 15 round and 9 wrinkled. That seems plausible as well. But what about this case, right? What if you grow a lot of plants, right? 120 plants, and you obtain 71 round and 49 wrinkled. But in terms of the raw numbers, what you expect is 90 and 30, right? You might ask yourself, wait, something is a little weird here, right? And you could even jack it up. You can multiply, say, for example, the number of plants by 10, 1,200 plants. Suppose you had 710 round and 490 wrinkled. You'd expect 900 and 300. You might say to yourself, I don't know, something's kind of going on weird. How do we measure this expectation and the deviation from expectation? All right. And so the way we do this, again, is using probability. All right. We're going to actually want to basically estimate what the probability would be if we observe such a weird deviation just by chance alone. That's the framework that we're going to want to think about this, because when we go back, we expect this, but this seems pretty reasonable by chance alone. So we wouldn't want to assign very low probability to that type of deviation. But we have very large deviations. We might want to assign a low probability to that deviation. So the way we do that is we have to do 2 things. One, we need some way of measuring the deviation from what we observe compared to what we expected based on Mendel's rules. And then 2, once we have that way of measuring the actual magnitude of the deviation, we need to be able to have a framework to determine what the probability of observing such a deviation would be. So, for example, if the deviation is small, we want to say, oh, that seems pretty likely. We want to have a reasonable probability associated with that. But if the deviation is huge, we might want to say, oh, the probability of just observing that by chance seems very small. And so we'd want to associate a small probability with that large deviation. Okay, and there's a way we do this. And we measure, in this particular case, when we're looking at ratios and outcomes. There are other statistics similar to this, but the deviation that we measure is called the chi-square test statistic. And what the chi-square test statistic is a summation for each of the categories of the phenotype of the observed number minus the expected number, and you square that, right? So you could be positive or negative, but once you square it, you become positive. You divide that by the expected number for each of the categories, and you sum up those deviations across all the categories. And so far, we've only been doing 2 categories. round or wrinkled, so on and so forth, but it could be more than 2 categories. So let's walk through some examples of this. So let's go back to the case where it's 2 to 2, 15 to 9, and 71 to 49. We're actually going to calculate up here this chi-square test statistic. Okay, so what I want to show here is this is just, category 1 and category 2, round and wrinkled, round and wrinkled, round and wrinkled. And so then what we did is we observed 2 and 2, or 15 and 9, or 71 and 49. And then these are the numbers that we expect. Obviously, the way you calculate the expected number is you calculate the ratio and or the fraction, the proportion, and you multiply it by the total sum. In this particular case, 4 or 24 or 120. So these are the numbers we expect. 3 and 1, 18 and 6, 90 and 30. We already talked about that. All right, so then what you want to do is you want to subtract expected from observed. So observed minus expected for each of the categories. So 2 minus 3, 2 minus 1. Okay, that's -1, that's +1. Or 15 minus 8, or 9 minus 6, -3, +3. 71 minus 90, -19, so on and so forth. And then we're going to actually calculate this summation is going to be the sum of a bunch of these statistics, but we need to do one more thing after we calculate that difference. We need to square it, all right? And then we need to divide it by the expected, which is this here. And so if you look in this column, we squared -1, so -1 squared is 1, and we divide by 3. We square 1, and we divide by 1 now, right? So 1/3 and 1. So here, all right, the deviation is -3. We square it. We get 9, and we divide by 18. Here we square this, we get 9, and we divide by 6. So each one of these values here measures that deviation basically by squaring the difference and then dividing by the expectation. Okay, so what you're going to end up with is, in this particular case where you observe 2 and 2, but you expected 3 to 1, you sum those up. So that's what this summation symbol here is, and so it's 1/3 plus 1 over 1, or 1. So the chi-square test statistic, where we didn't see much of a big deviation was 1.33. Here we add those two up, we get 2, but this one's big, right? Because we have a big deviation, -19. We square it, we divide by 90, so 361 divided by 90. Here we get 19, we square that one. We divide by 30. So the sum of this one is big. It's 12. This is 1.33. This is 2. And then this is about 12. So what do we do with that? I'm going to go back to that point that we have a way now of measuring deviation. The bigger the difference between observed and expected, the larger this chi-square statistic is going to be. All right? But how do we figure out this probability of large and small deviations? Okay, and the way we do that is we use something called a p-value. And a p-value, and you should remember this definition, so we will see other definitions out there, but the p-value is the probability of observing such a big deviation from what is expected by chance alone. You're going to get deviations from expected. You're not going to always see a 3 to 1 ratio, but when there's a big deviation, that is going to give you a low probability, and so we call the p-value the probability of observing such a deviation. Now, this is some sort of feeling that you should get for the p-value. If the p-value is very, very low, then the probability of that event happening under the null hypothesis is also very, very low. And this is somewhat arbitrary, if p is less than 0.05, we consider that low enough to reject the null hypothesis. The null hypothesis is the predicted ratio in this particular case, where it's 3 to 1, which is what we've been working in here. If we get a low probability, that means the deviation is large, the probability is low, and if it's lower than that threshold, we reject the null hypothesis of a 3 to 1 ratio in this case. Okay, how do we get the p-value? All right, now we use, in this particular case, something called the chi-square distribution. Now, we're not going to get down into the weeds on this, but I want you to sort of know where these things come from. If you take an advanced statistics class or an advanced probability class, you would learn this. But for now, we don't need to worry about the details. But for now, this is what a chi-square distribution looks like. All right, it's a complicated equation, and it has a parameter in it, in this particular case, k, which indicates the degrees of freedom. So, but basically it has these different shapes, and these are probability distributions, okay? So degrees of freedom is 1, degrees of freedom. These are parameters of the distribution, but you don't need to worry about like how they fit into the calculation, but I will explain degrees of freedom momentarily. Okay, now, for a chi-square distribution, in this particular case where degrees of freedom is equal to 3, what is the p-value? Okay, the p-value is the probability on the chi-square distribution of getting such a large value of the chi-square test statistic. Okay, so the chi-square test statistic can go from 0 down here to very, very large up here, right? And what the p-value is where that chi-square test statistic sits. It's actually the area under the curve above this, okay? Now, if chi-squared is 0, all right, it's all the way down here. If chi-squared is 0, that means we actually had no deviation. And the area of the curve above that, in this particular case, would be the area under the entire curve. Now, this is the probability distribution. Probabilities add up to 1. The realm of all possibilities will add up to 1. So when chi-squared is 0, the probability or the p-value will be 1. As chi-square gets larger and larger and larger and larger and larger, the area under the curve gets smaller and smaller and smaller. And this is all done with calculus, but we don't need to worry about that because what we're going to use is a chart. And we're going to use something called the critical values of the chi-square distribution. Because what we want to do is calculate a chi-square and ask if we see a p-value that is consistent with the null hypothesis or suggests we should reject it. Now, the way we want to read this table here is in this column here we have what are called the degrees of freedom. Now the degrees of freedom, as I showed you before, determine the shape of that chi-square distribution. But for our purposes, what you need to think about with respect to the degrees of freedom at this moment in the class is that the degrees of freedom is equal to the number of phenotypic classes minus 1. So where we have 2 phenotypic classes, round and wrinkled, the degrees of freedom is equal to 1. We'll use different degrees of freedom later, but for the purposes of right now, just think about it that way. All right, so we're going to pick right here, degrees of freedom equal 1, and these are going to be p-values. These are going to be chi-square test statistic values. Now what I want you to look at here is up above p, those are the p-values. Now we're not going to get an exact p-value from using this chart. You can use a computer to get exact p-values, but right now we're not going to get exact p-values. Now notice something here. This row here for degrees of freedom is equal to 1 are the chi-square test statistics that you might calculate. And you can see that it goes on this side larger and larger and larger. Those larger and larger chi-square test statistics indicate smaller and smaller probabilities. Okay? And so we would actually calculate the p-value. Now, you're not going to necessarily have exactly 6.635 or 7.7879 for your chi-square test statistic. So I'll show you how you're going to estimate p-values by providing bounds in the next slide. Okay, so in this particular case, we did those 3 chi-square calculations. The first one was 1.33. The second one was about 2, I think exactly 2, and then the last one was about 12. Now, there's 2 ways you can do this. The way that I've done it here is I've provided estimates, okay? So 1.33, all right, we're going to actually look here and we're going to say, okay, where does that lie, right? And we say, oh, it lies somewhere in between there, all right? Now, it's going to be closer to this side, and so because it's bounded on this side, our p-value, we would say, is greater than, because it's greater than this bound, right, because it's between here and here. It's greater than 0.01 because it's kind of on that side. All right. Now you could say it's greater than 0.01, or you could say it's between 0.5 and 0.1. Sorry, I think I said 0.01. I meant 0.1. So you could say it's about, greater than 0.1, or it's between these two numbers. That's fine. All right. What about 2? Well, it's actually a little bit closer. It's more like 0.15, but you could say it's still greater than 0.1. Okay. Now let's go to the case where the deviation was huge, right? So now we're off the charts, like literally, right? Because our chi-square test statistic is like way beyond 7 point that. And what you could do is you could say, okay, well, this puts me at a p-value which is lower than that one. So I can say it's less than 0.005. Actually, technically, it's even closer to it's even lower. It's 0.0005. That's a calculation I made. But you provide the bounds. But the critical point here is that this is less than this threshold. This is 0.05. Our chi-square test statistic is larger than 3.841, and therefore the p-value is less than 0.05. So here we do say we reject the null hypothesis, and where we got 71 and 49, we can say that we reject the 3-to-1 hypothesis. So remembering that the threshold is 0.05. Okay, now continuing on with probability, up until now we've basically been saying like, okay, we have these events that are independent of one another. So the probability of getting, a boy after having 7 boys in a row is still a half, right? Or the probability of getting round given 5 wrinkles in a row is a 3/4, right? Now, in those cases, all of those probabilities didn't depend on anything. They just sort of were independent of each other, right? But sometimes we have scenarios where the probability of an event given another event happened when the events are not independent, all right? And so I will give you a couple examples you can think about as what is the probability of event A given some circumstance B? Or you could say, what is the probability that a child is affected by a disease if the first child is affected? That's kind of the framework that we're going to be working through, and we're going to do some stuff on the board right now. Okay, so I'm switching to the board here. And there's from previous lecture. I'll erase that. Now, we'll oftentimes estimate a probability based on some circumstance. And so the way we can do that is we can ask, and I'll just basically provide sort of a framework here. You can say, what's the probability of an event A? And we're going to use a line here to say given some other circumstance like B. All right. Now, we could ask, for example, about a family in which there is a child that has autism. Now, in the case where a family has a child that has autism, we think that there's a pretty strong genetic component to having autism. So you could ask, for example, if the first child has autism, you could ask, what is the probability that the second child has autism, given a situation in which the first child has autism? So in this particular case, this event is sort of telling you that maybe something is going on. Now, one thing that I want to be a little bit clear about is we've already kind of been doing a form of conditional probability, but it's been implicit, and I haven't been making it explicit, all right? So, for example, if we have big R, little r, or sorry, actually, we've been using big W. You can go back. If you have big W, little w, and you self it, all right, and we're saying, okay, what's the probability of obtaining wrinkled? All right. Well, actually, in some ways, we've really been doing what's the probability, let's just, of obtaining little w, given this condition. And what's the condition? Well, it's that we have progeny from big W, little w selfing. So this sort of condition has been kind of in the background all this time. All right. Now, we've already been saying that when you have the probability of A plus the probability of not A, what do those add up to? All right, well, those add up to 1, right? That's like the realm of the entire world, all right? And you can actually imagine like the realm of all possible outcomes. It's sort of like a space here in which the area is equal to 1, right? So this is the realm of all possible outcomes in any sort of arbitrary scenario. And so, this we could say the area of this space is equal to 1. Right? And you can kind of think about what we've been doing here now. If this area is equal to 1, maybe you can break that area. And this is why the probability of A plus the probability of not A equals 1. This is all going to be equal to 1 here. Well, you can break that up into, say, for example, the probability of A. And what's over here? All right, well, that's the probability of not A. Okay? And you could break the probabilities on which is arbitrary A and not A. We've been doing boy and girl, for example. If we get rid of that and just say, for a given family, like just the first child, right? The probability that the first child is a boy, and this is the probability that the first child is a girl. Well, in this particular case, we've broken up the world where all of the outcomes equal to 1 into 1/2 and 1/2. All right. Now, of course, you can do it like this, right? You don't have to do it with boys and girls. You could do it with round and wrinkled peas, right? You could say, okay, well, I have a selfing, big W, little w, and I can break the outcomes up sort of visually like this, right? All right, so this is 1/4, this is 1/2, this is for the progeny, this is 1/4, and this would be big W, and this would be big W, little w, and this would be little w, little w. So again, I'm kind of breaking up the world of all possibility into this sort of broken down framework. Okay, now you could do something here where you could actually pick one of these progeny. Okay, blind, right? You close your eyes, you don't look, and you could pick the progeny. You either pick this one or this one or this one. You don't know what it is, and you could self that, right? So I don't know which one I'm going to pick. I'm going to pick one at random, and I could self it, and then I could say, well, what about the outcome of that selfing? All right. Now there's an intuitive kind of way you can think about this, right? So what we want to know is like, okay, I'm going to pick one at random. I'm going to straighten this out a little bit. You're going to pick one at random. Pick one at random and self it. All right, and then I could ask the following question: if I pick one at random and self it, what is the probability that I obtain wrinkled? Okay, and what I'm going to do now is I'm going to kind of like jump forward and then I'm going to jump back, all right? And I'm going to jump forward to sort of walk through how I would do it, and I'm going to use that as a framework to explain something that we're going to call the law of total probability, which is an important feature of conditional probability. Now, if we pick, we said we pick at random, and we just want to know the generic thing is if we pick one at random, what's the probability of obtaining wrinkled? Now, you could actually just ask one by one, okay, well, if I pick that one at random, the probability of obtaining wrinkled if I solve that one, all right? So this is sort of a conditional, right? Given that I picked this one, I could say the probability of wrinkled given I picked big W, big W. Now, if this individual is big W, we're selfing a homozygote, okay, well then the probability would be 0 here, right? And then what's the probability that if I picked one of these, that I get a wrinkled one? All right, well, it would be, probably, I don't want to screw this up. Probability that I get a wrinkled one in that particular case would be a quarter, right? And the probability that I get wrinkled with this one, all right, would be 1, right? Because it's like that, right? So you can kind of say like, okay, well, I want to actually figure out this thing here. And you could say, well, what I need to do is I basically need to weigh these probabilities based on the chance that I actually ended up picking that, right? And so what you can do is you can kind of break it down this way, right? You can say, okay, and this is the sort of intuition that I'm going to give, and then I'm going to formalize it. You could say, well, the probability that this ended up being wrinkled is 0, and the probability that I actually picked that as a quarter. So you could say, well, this contribution to that probability is going to be equal to 0, which can happen, times the chance that I actually picked that one, a quarter. Right? And I'm going to add that now, and this is going to basically, because things can be mutually exclusive, and you can add things, I'm going to say, well, there's a half chance that I picked this one. No, sorry, I'm saying if I get that, there's a 1/4 chance that I end up with a wrinkled one, but I need to weigh that by the chance that I actually picked that heterozygote, and there was a half chance for that, right? And then this one here, well, here I'm guaranteed to get it, so there's a 1 chance, and then but there's a 1/4 chance I actually picked that in the first place. All right, and so if you add those up, so this becomes 1/8, and this is 0, and then this is a quarter, or 2/8. The whole thing is equal to 3/8. And so, as I said, I kind of jumped forward a little bit, but the way you would do this, and the way you think about this, is you say, okay, if I just pick one at random, I need to basically say, what's the probability I picked any particular genotype? And I'm going to multiply that times the probability that I did get that wrinkled one under that circumstance where I picked that particular genotype. Okay, so now I want to formalize what we're doing here. All right, what we are really doing in this particular case is adding up and saying that the probability that we obtain wrinkled all right, or little w, all right, is equal to the probability of obtaining little w. I'm going to use a little bit of shorthand, right? Given that I picked big W, and I'm going to multiply that times the probability that I picked big W. And I'm adding that to the probability that I get little w, given that I picked big W, times the probability that I picked the big W, the heterozygote. And then I'm adding that to the probability of getting little w outcome, given that I picked Now this is the homozygote little w, all right, times the probability that they actually picked that. Now, as I said before, this looks like a little bit of a jumbled mess that I'm jumping forward to, and you might be saying to yourself, like, where does this come from? And where this comes from is something called the law of total probability. Which is going to be something you're going to use. The law of total probability. And the law of total probability states that if, this is going to be more general, all right? We have a bunch of events, I'm going to just call them 1, 2, 3, 4, so on and so forth, right? If probability of event 1 plus the probability of event 2 plus the probability of event 3, right? Dot, dot, dot. So it can be in any number of possible events. So I'm going to say all the way up to n, right? If this equals 1, right? And one and 2 and 3 dot 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 n are mutually exclusive. All right, are mutually exclusive. Then, all right, and this is any other arbitrary probability, right? Then the probability of anything, let's just call it A, is going to be equal to, and it's going to be the probability that A happens given I'm under condition 1. So given 1 having happened, times the probability that 1 happened, plus the probability that A happens under some other circumstance, say for example 2 happened, times the probability of 2 happened. I think you can see where this is going. Plus, go down here, the probability that A happened given scenario 3 times the probability that scenario 3 happened plus dot 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 the probability that A happened given that last scenario n times the probability of the last scenario n. Okay, now that looks like a bit of a bear, and that's a formal presentation of it. Okay, but what I want to basically use is a couple examples so that you can kind of think about it, right? And the first one is going to be the condition of getting lung cancer. Now, you know that getting lung cancer depends on something, okay? It depends on something, and that something is whether you smoke or not, right? Because of that, you can break down the probability of just getting lung cancer in general into 2 separate subpossibilities. And you can basically say the following. The probability that you get lung cancer, and this is using the law of total probability, is going to be equal to the probability that you get lung cancer, all right? And this is sort of this, like, I'm going to just formalize this. You can break this down into a very simple version here, all right? You can also say, you know, I said, oh, A given 1 and A given 2 and A given 3. You can also say that the following. You could also say that the probability of A is equal to the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B, right? Because this is this B thing here, the probability of B plus the probability of not B is equal to 1, and those are certainly mutually exclusive. Right? So this is a simpler version of it, where you just break it, in the first case I had like 1 and 2 and 3 and 4. Here it's just like B and not B as the two mutually exclusive conditions. Now we can say the probability of lung cancer, this is kind of like A here. All right, we could say that this is A here. Probability of getting lung cancer given you're a smoker times the probability that you're a smoker. Right? This is like B here, right? If you look up here, the probability that you get cancer is equal to the probability that you get, lung cancer, given that you're a smoker, times the probability that you're a smoker, plus the probability that you get lung cancer, given that you're not a smoker, times the probability that you're not a smoker. What does it mean, the probability that you're a smoker or not a smoker? Well, in a population, it depends what the frequency of smoking is for any random population, right? So this might be different, say, for example, in one country versus another. All right, so this is going to be added to the probability that you get lung cancer, given what? That you're not a smoker, that little minus being not, times the probability that you're not a smoker. Okay, so that's a general framework. You can kind of do it. I just want to keep the analogies going a little bit to sort of the visual analogies going. You can kind of think about it also as like this way. You have a day, and you want to say what's the probability in Lawrence, Kansas, any random day that it's above 90 degrees. All right, well, you could say, well, that's definitely going to depend on the month. It's also going to depend on the exact day, but let's just break it down to the month. You could sort of say, like, okay, and let's just be simple. Let's just say, there's just 12 even sectors. All right, we're not going to say, oh, February is a little shorter. We're just going to say, like, the entire year can be broken up into January, February, March, April, so on and so forth. Well, I'll just do the whole thing. April, May, June, July, August, September, October, November, and then December. All right. Now, a visual way of thinking about, you could say, okay, what's the probability that any random day is above 90 degrees? Well, you could say, well, that's equal to, right, the probability that you're above 90 degrees, given that it's January, times the probability you are in January, right, which is, let's say, 1/12, plus the probability that it's greater than 90 degrees, all right, given that you're in February, times the probability that the month that you picked, the day that you picked, actually ended up being in February. You can see where it goes there, right? You can just, and actually, like, visually, you can kind of think of it as like, okay, in January, it might be really low. Like, the proportion of that might be almost zero, right? And the proportion is going to stay really close. But March, well, it might get a little bigger. And then April, and then May, it might get to be, maybe not that high, but June, it might get to be pretty high, right? July, August, that's going to be high. September is going to be high. And it might start going down here. November, December. What you're doing here is you're saying, each of these is 1/12, right? And you're multiplying each of these 1/12 by the proportion of that area of that month that would be satisfying the condition that it's above 90 degrees. All right, so that's sort of another graphical representation of it. All right, I'm going to check one thing to see if that is the end. Okay, we're going to do a few little problems to think about to get the juices flowing, and then we'll be done. All right, so in this particular problem here, Okay, we pick one of those round plants and self it to yield one progeny. What is the probability that the progeny of this selfing is round? All right. So we want to say the probability. All right. So just to be clear about this, we pick one of these from the F2, right? Okay. What is the problem? So the first thing we want to do is we want to formalize that. Okay. We are picking the big. Well, I switched from big W to R here. It's an old slide, so let's just do that in here. Let's R be, that one's round. This one is round. And then little r is wrinkled. I've switched it up because it's an old slide and I haven't yet purged the R's from all of this. But anyway, you pick one of those round plants and self it. What is the probability that the progeny of that selfing is round? Now, one thing that's worth keeping in mind is, since you picked one of these, all right, and you're selfing that, obviously, like if you self that one, you're never going to get a wrinkled one, right? So, that's guaranteed. But if that one ends up being the one that you picked, you don't know which one it is. So let's actually just formulate what is the probability that the progeny of this selfing is round. Let's just do the framework here. Think about A, B, C, or D here. Which one would it be? Most using the law of total probability. Again, we're not putting numbers to it, but just think about it. Okay, well, D would be the right answer here. All right, so you want to use D here because, just to sort of break that out a little bit, the probability that we obtain a round one, it's going to depend on who we pick, right? We know we picked one of these round ones, but we're going to self that. And the probability that we end up, and we're going to just say the probability that we end up with big R dash, right? Because there's two ways of getting around, big R, or big R, little r. Given that we picked a big R parent, the F2, times the probability that we actually picked that one, plus the probability that we obtain big R dash given having picked now the other possible F2 here, big R, little r, times the probability that we picked the big R, little r. All right. So that's it. Okay. Let me just bust ahead for a second here. Okay, there's a couple more problems that we're going to do. I think I'll save the very last one for Tuesday in class. What is that probability? This is actually some important things that you want to get at here. Okay, so if we pick the big R, so we're going to break down, we're going to start plugging numbers into our equation here, all right? So I realized I didn't put the screen on here, so I'm going to go back, all right? So what I just walked through here is the probability of obtaining round is the probability for D here, the probability of obtaining the round one given having picked the big R parent times the probability of picking the big R parent plus the probability of getting a round one given we picked the heterozygote plus the probability of actually having picked the heterozygote. Okay, so we're going to put some numbers to this now. All right, now the probability that if we actually pick this F2 here, then it's going to be 1, right? So 1 is going to be, it's guaranteed, right? Because if we self that individual, it's definitely going to get round, right? Now, if we pick this one here, the probability would be 3/4. Okay, now this is actually going to be a tricky part here that I want people to make sure they understand. All right, what's the probability that I actually picked the big R, or I picked the big R, little r. All right, so I'm going to do some work up here. Now, in the context of the Punnett square, okay, big R, big R, little r, because I did a selfing there, okay, but I picked the round one. All right, so 1/4 chance of big R, 1/4 big R, 1/4 little r, big R, and then 1/4 little r. You might be inclined to say, oh, the probability that I actually picked that big R genotype to self, the probability is a quarter, all right? But it's not a quarter, and there's a subtle reason for that. The reason is actually I know for a fact that it's not this genotype because I'm not picking a wrinkled one. I'm picking a round one. Okay, so what is that? Well, among these ones here, what proportion have that genotype? Among those ones here, it's not 1/4, 1/4, 1/4 because then that wouldn't add up to 1. Of all of those, 1/3 of those are big R, and 2/3 of those are big R, little r. So that's a subtle thing that you'll have to remember. If I tell you that I picked a particular phenotype, then you have to rethink about what the possible genotypes are. All right, if I tell you I just pick one at random without respect to the phenotype, it'd still be what it was before. But if I told you I specifically picked against the wrinkled ones, then now my proportions are going to change. So this would be 1/3, and then this would be 2/3, and you would multiply that out to answer the question that was on the slide right there. All right. All right, that would be the way you would follow through and get the full probability. Okay, so if you were to do that, what is the probability that the progeny of this selfing are all round? All right, so if you picked one random plant and selfed it to yield 4 progeny, the way you would do this, and I'll leave this as an exercise for you that we'll continue on, is that you would basically figure out for any particular one, so it would be 1/3 plus, so that's this top part, and then 3/4 times 2/3, and that whole thing becomes 6/12 or a half. So this becomes 1/3 plus a half, and now I have to sort of change this into 2/6 plus 3/6, so we get 5/6. That's a probability that if I pick, let me make sure I did that right. 6/12 is a half and a third, and then this becomes 2/6 and 3/6. Yeah, 5/6. That's a probability that I would obtain for any one of them around pea plant. But I'm asking about if you self it and yield 4 progeny, what is the probability that all the progeny are round? Well, then it would be 5/6 to the 4th. All right, so that would be that for that one. And then, went in the wrong direction. We will work through this problem in class. But I want you to think about it. The brother of a man with an autosomal recessive disease has a child with a carrier of the disease. What is the probability that their child will be affected? So we're going to actually walk through and talk about that on Thursday. All right. Thank you very much.